Hello, everyone. My name is John Wise, and I'm going to present a plugin I've been working on for the last few weeks. My goal with this project was to learn the plugin development framework called JUCE. So doing a quick Google search, I found a free code camp video on YouTube and started coding. Now let's talk about SimpleEQ. SimpleEQ is a 3-band filter plugin consisting of a low cut, high cut, and peak filter. The low-cut filter attenuates frequencies from 20 to 1000 Hz and has a controllable roll-off of 12, 24, 36, and 48 decibels per octave. The high-cut filter attenuates frequencies in the range of 1000 to 20,000 Hz and has a controllable roll-off as well. Lastly, the peak filter is capable of boosting or attenuating frequencies from 20 to 20,000 Hz. The peak filter also has a controllable quality parameter which gives the user the ability to dial in the bandwidth of the filter. Each filter has an associated bypass button, which allows the user to toggle the filter on and off to better understand how the filter is manipulating the source signal. One other big section to note is the spectrum analyzer portion of the GUI. The spectrum analyzer presents spectral information of the left and right channels of the source signal. It also graphically shows the characteristic of each active filter. In this presentation, we'll focus on the audio processor part of the plugin, but there was quite a lot of work done to the GUI as well. The spectrum analyzer utilized an FFT algorithm to produce the FFT path. We won't get into it here for time's sake, but if you're interested in how we implemented this, you can check out the YouTube video linked at the end or explore the source code on GitHub. With any project like this, where I'm learning a new technology, I like to synopsize what I learned and then integrate it into the broader scope of things I already know about DSP. That way I can relate the new knowledge with broader concepts I already understand. With that, let's discuss how a DSP filter works for a moment. You can find this information in my full-length blog post, How DSP Filters Work, which is linked at the end of this presentation. For this project, we used an infinite impulse response, or IIR filter, for each filter. We know that these types of filters have some number of feedback paths in their schematic as shown in the picture. The filter diagrammed here is a first-order filter, so the difference equation is very simple. Two questions naturally arise from this. One, what should the values of the coefficients A0 and B sub 1 be? And then second, how do we relate these coefficients to the parameters that we allow the user to control, notably cutoff frequency, roll off, etc.? We would want some sort of equations which can be used to transform these input parameters to the coefficients of the filter. In this project, we used a high-order Butterworth method filter built in the JUCE framework. In this snip, we can see the equations which use cutoff frequency and sample rate to determine various coefficients of the filter. This is more than likely not the exact equations that JUCE is using, seeing that this is a second-order filter, a biquad filter to be exact, and the order of the filter that we're using in JUCE goes up to the fourth order. So I imagine that they're different, but the concept should translate. Now that we have reviewed some things that we know about DSP filters, let's talk about the code. The plugin processor is the heart of the JUCE plugin. It is where the plugin defines the functionality required to prepare for audio processing and perform the signal processing algorithm. The main methods defined in this class are the prepare to play and process block functions. The audio processor value tree state variable member, APVTS, defines the parameters used by the DSP algorithm. Left and right channels are processed through their associated monochains, which are instances of the JUCE processor chain class. In broad strokes, the processor chain allows you to chain processors together in series. When the process method is called on the chain will iteratively call the process method on each processor in the chain. In our case, we chain together each filter for both the left and the right channels. So when the process function is called on our left chain or right chain, we iteratively call the process function on each filter. Okay, now let's talk about the prepare to play method. The prepare to play method defines and instantiates a JUCE process spec object. The process specification defines the sample rate, block size, number of channels to be used in the DSP algorithm. This method also calls the prepare method for each chain, which prepares all interprocessors in the chain with the provided process spec value. We created a function to update all 3 filters. This update function grabs the chain settings from the APVTS and updates each filter. Updating a filter consists of recalculating the coefficients of the filter according to the parameters set by the GUI. Here is a quick snip of the source code for the prepare to play method. Going on to the process block method, the first step is to update the filters and make sure that their parameters agree with those values in the APVTS. Next, we create a JUCE audio block for the left and the right channels from the buffer parameter that's passed to the plugin by the host DAW. We use those to make a process context for the left and right channels. We pass the left and right context to the process method of each chain, which processes each block through the filters we've defined in the chain. Lastly, for the FFT spectrum analyzer port of the GUI, we process the blocks through our FIFO queue so that the FFT will have the data necessary to make the FFT path. Here we can see the process block code. Now, let's hear the plugin in action. All right, so this is our GUI. You can see we have our low cut filter here on the left. In the middle shows our peak filter, and on the right we have our high cut filter. You can see this white line shows the each one of the filters together. If I disable the peak filter, you'll see that peak go away at 750 hertz. Similarly, if I disable the low cut filter, you will see this low cut go away as well. Let's play some audio through it to kind of get a sense of what we're hearing. We'll start with no filtering at all. Thank you all for watching to the end. I left some links to resources here at the end of my presentation in case anyone would like to dive deeper. Until next time, cheers!